प्रोसेस एडियाबैटिक ले रहे होते हैं, लेकिन चेंज इन इंटरनल एनर्जी हम वो लेते हैं जिसको कि आइसोथर्मल प्रोसेस के लिए इस्तेमाल करते हैं। तो ऐसा हम क्यों कर सकते हैं? क्या हमें ये करना जायज़ है? इज दैट परमिसिबल? Taking adiabatic processes, considering adiabatic processes, but then taking U equal to, or du equal to n times Cv times dt, which was calculated for constant volume process. Okay? Some people are still worried about some other thing, talking to each other. All right. So is it valid to take a form for u or du which was derived for this particular process? And I think the answer was, which I tried to explain last time, but let me say this again today, lies in the fact that u is a state function. U is a function of state, and therefore it actually is something which is defined for a given state of the system. If in a state space a point is here and a point is here, then u is defined over here and u is defined over here. This is u1 and this is u2, and du is u2 minus u1, whatever the process. Because this is a state function, therefore whatever the process, change in u will be the same. So we can take a very convenient path which helps us solve the problem. And this is actually what we did in the example that we did last time for calculating entropy change. We argued exactly this in exactly the same manner. We said that entropy is a function of state because ds over a closed cycle is equal to 0. So entropy is a function of state. Change in entropy doesn't depend upon paths, and we were faced with a situation where we were looking at an adiabatic process, and in an adiabatic process dq is equal to 0, whereas ds was defined as dq over t, and we didn't know how to get the value of change in entropy in an adiabatic situation. So we argued in the same way. We said that entropy is a function of a state. A change in entropy would not depend upon the path you adopt. It would be the same for all the paths. And therefore we chose a convenient path in the last lecture. And that convenient path was an isothermal path. And through this we were able to get the result. The result we got last time was very significant, and I think that is going to be something we will discuss later on. The consequences of this we will discuss later on was nRT times log 2. This was the expression we derived last time, and this log 2 was a result of expansion. Oh, T नहीं था इसमें. Okay, T was this was heat change. So You are right. NR times T. It can't depend upon T. Log 2 as this expansion to a double volume. V2 was equal to twice V1. It is because of this 2, this doubling of the volume, that this 2 appears over here. And this is, so the conclusion was that we had a gas confined to a half of the container by means of a divider, partition, and then we remove the partition, allow the gas to spread to the entire volume V, and when we do that, other things will happen. Temperature will not change, volume will double, and other things will happen, but the entropy actually changes by this much amount. There is no work done, there is no change in internal energy, there is no heat exchanged, temperature remains the same, but then the entropy changes by this amount. So what is the fun? कुछ हो रहा है यहाँ पे, तमाशा हो रहा है कुछ? किधर से आए? मेरी रिकमेंडेशन पे आने दें इनको, मेरी स्पेशल रिकमेंडेशन है, आने दें इनको. ओके. Such ardent seekers of knowledge. How can we keep them out? Okay. The other point which bothered most of you was the relationship between entropy and heat capacity. People came to me afterwards and said that both of them had the same dimensions. Heat capacity is Q over T, and you say entropy is also Q over T. So what is the difference between them? Isn't entropy the same as heat capacity? My answer the last time was, but today I will try to be a little more, I will elaborate a little more. My answer was that heat capacity was very, very specific to a substance. It is it is a specific property of substances. And under given conditions, if you increase temperature of substance, it will accumulate certain amount of heat into it. Or if you give heat to it, its temperature will rise by a certain amount. And different substances show different behavior with lesser or greater increase in temperature as you supply equal amounts of heat to different substances. So this cannot be a state variable. It cannot be a variable. It is a peculiarity of the system. It cannot be a state variable. However, entropy turns out to be a state variable, a state function. A function of a state which we said satisfies this particular property. Heat capacity does not satisfy this particular property. Okay? And therefore, state of a system, a thermodynamic system, will have to be specified in terms of various variables, one of them being entropy. Okay? That is a largely the main difference between them. Mathematically also, when you write heat capacity, you write heat capacity as some amount of heat given to the system divided by some change in temperature, but limit dt going to 0, dt going to 0, is how you define heat capacity. And then this quantity, when you try and calculate this, the path of this becomes very important. And this path of it, in which we notice that there is CV and there is CP at constant volume and constant temperature. In the case of entropy, we in fact take entropy change ds as dq by t, not dt, and you rewrite this as c times dt by t. C is heat capacity. And because of this, heat capacity at constant volume becomes T times partial differential of S with respect to temperature at constant volume, and partial differential of pressure, Cp, constant heat capacity at constant pressure, becomes the same with pressure being kept constant. This should be taken as a difference between heat capacity and entropy. Dimensionally, there is temperature in the numerator and temperature in the denominator, and therefore the dimension of entropy would be the same as that of the heat capacity. But this is a state variable. Okay. So I've explained these two things. Important difference. I will take up just one other important, interesting point before I move on to my further discussions on the question of entropy. And this is about the point that while if you take a heat, variation of heat over a closed cycle, even on a reversible closed cycle, this is indeterminate until the path is specified. We have been talking about this over here. Okay? While this is the case, dq by, you see, I have again been not very particular with putting a slash on the d of when I describe changes in heat. Some people are very particular. I often don't care about it, but still. This by t is determined completely without a path, without specifying a path. This is the difference between them, and we need to understand what is happening over here. A very minor point, not terribly startling point, but it is interesting. And I thought I should bring it to you. I read it somewhere and I liked the point, and I thought I should share this point with you. The first law is du equal to dw plus dq, and in a quasi-static process, we can write this as minus P dV plus dq. You all agree now? And since, as I said, for an ideal gas, if I have an ideal gas, then du is, as I wrote over there, Cv times dt for 1 mole, say. Or Cv is not molar heat capacity, but the total heat capacity at constant volume. And I said I can use it anywhere because as far as u is concerned, it is a state function, so I can. So that actually amounts to saying that dq is equal to Cv dt plus P times dV. Okay, I just plugged in this value on the left hand side and rearranged the terms. Now if you try to integrate this value to get the value of q, q will be equal to dq. If I try to integrate this, it will be integral of Cv dt plus integral of P dV. And here we can take, for example, Cv to be constant. Even if we take Cv to be constant, so that this part can be integrated, this will become Cv times T2 minus T1 or T final minus T initial. But here we will not be able to do the integration unless we know a relationship between P and V. Unless we know a relationship between P and V, we will not be able to solve it. Either we say that P is constant and take P out and do the integration, which is fine. But then by saying P is constant, we actually have specified a path, isobaric path. So we have actually specified a path over here. Or we write down the equation of motion, equation of state, which is that from P, if you know that PV is equal to RT, then I can write for P RT over V, and then I will have this as R integral T dV over V, and even here I will need to specify what to do with the temperature T inside the integral. Do I take it constant or do I not take it constant? If I take it constant, I specify the path. So I have no recourse but to specify the path if I want to solve this integral. Okay? On the other hand, if I were to take, sorry, your question is?
Are we taking number of moles equal to 1, nRT?
Well, that is unimportant at this time. I can take n equal to number of mole equal to 1, okay? As I did over here, or maybe over here also, and I could put in n if you like, but that is not going to change the discussion point. So over here then I can now try and actually calculate something else. I calculate integral dq by t and see what comes out. This will be integral Cv dt over t and then plus integral P over t dV. Okay? And as before, not as before, but this time, it will be Cv times log of T2 over T1, because this will be dt over t. If I take integral, it will be log t, and log t is going from T1 to T2, so this will be log T2 over T1. Okay? I hope when I go through such mathematics, it is not terribly obscure for some of you. I mean, if it is, stop me, then I will raise your hand and I will go through it in detail. Okay? And then the second part is actually over here very clear. It is P over T. And from the equation over here, it is R over V. So this is actually R over V times dV. And this R over V times dV would again be easily solvable. This will be R times log of V2 over V1. Okay? I can perform integrations now without specifying any path. Okay? This I thought was a beautiful point. It tells you what the difference between dq and dq over t. dq is path dependent, dq over t is not path dependent. See this particular example. And I thought I would share this part with you. Okay, the last time I took an example, as I said over here, of a gas being initially confined to this area and then being let out to fill the entire volume or increase from V1 to 2V1. And then we calculated and we found that change in entropy was equal to this. Okay? Let us take another example and work through this. And over there again, what we will need to do is to calculate entropy change, we will need to sort of go through some processes which will be trying to find an alternate ways of doing things. So in this particular case, as I said, we had an adiabatic expansion, but we found out this value through an isothermal process. And we justified it by saying that S is a state function, so it doesn't really matter how you go from point 1 to point 2, right? I think I have sort of repeated this statement so many times that it should be a part of your general understanding of how state functions should be treated. Okay? This second example is again very interesting. It says, and again, an example of an irreversible process. And we will eventually come to some conclusion about entropy and processes being irreversible. That will be a very important conceptual leap for us. That will tell us that irreversible processes are the ones for which we worry about the function called entropy. Had it not been for that function, we would not know how to specify, how to differentiate between a reversible process and an irreversible process. And we notice all around us that our life is submerged into irreversible processes. And therefore entropy is something which is all around us. Not quite easily seeable, or but then we can get to the point where we can try and understand what entropy is. So this is a good example. Again, in an adiabatic situation, there is this initial situation where there is this completely sealed box, insulated box, and this box has a partition which is again insulating, and you have a block of metal here and a block of metal here, both of them perhaps of the same mass, the same material. Mass, both of them have the mass m, and I should write larger. Is it a large enough diagram for the people at the back side? Okay. So mass of each one of them is m, and heat capacity of each one of them is C. We don't have to specify with the subscript V or P, just heat capacity is C. And then we say that this was the initial condition, and you wanted to get to a situation where within the same box I remove the partition and allow the blocks to, this block is at temperature T1 and this block is at temperature T2. I should mention this. They are at different temperatures in their respective boxes. And then they are allowed to come into contact with each other. And obviously, when they are in touch with each other, heat will flow from the hotter body to the colder body, and they will come into thermal equilibrium, and there will be a final equilibrium temperature. All right? And the final state, therefore, this is the initial state, and this is the final state. And this will be an equilibrium temperature with a subscript E going with it. Okay? So this is an equilibrium temperature. In this process, what happens to entropy? We should try and work out. Okay? Now, the temperature of block 1 will go from T1 to TE. Let me also start by saying that T2 is larger than T1. Okay? One of them is larger, one of them is hotter than the other. Therefore the heat will flow, otherwise the heat will not flow. And T2 is larger than T1. So T1 will go to TE and T2 will also go to TE. And we should try and this process, when it happens, when you bring the two together and let them sit with each other, they will certainly exchange temperature very rapidly in some manner. But that particular process of exchanging heat with each other can be a, I'm going to use the term, non-equilibrium process. But it will sort of not be quite an equilibrium process. Equilibrium process is when a thing is allowed to rest, it will rest in that state unless you act upon it. Otherwise, it will just be in that state. Whereas this will not happen. I mean, there will be a lot of heat flow from one side to the other. And that heat flow will be something which we will not be able to measure. We will not be even able to define temperatures in the middle, because it will be all sort of heat going from one side to the other, and kind of a non-equilibrium situation. For that, we will not be able to. This is P, and this particular process of temperatures going this way and that way is an irreversible process. Irreversible in the sense that you can't separate them out and they will again, one will go to temperature T1 and the other one will go to temperature T2. That just cannot happen. We all know that. Okay? So this is going to be an irreversible process. What we will do to find out the change in entropy is to turn this irreversible process into a reversible process, or a quasi-reversible process. So what we in fact at times use the word quasi-static process. Quasi-static process. Quasi-static process, I think I explained earlier that quasi-static processes are all supposed to be reversible processes, because in a quasi-static process changes take place only very minutely, and then after every change the system sort of comes to an equilibrium first and then moves on to the next step, and therefore it sort of remains in equilibrium all the time, and it is a process in which you do not quite face the problem of getting into a non-equilibrium situation. Alright? And therefore we will try and turn this into a quasi-static problem and try and solve it. So let me try and do this over here. So we will say that the quasi-static process that we are thinking of the temperature T1 goes to temperature T1 plus delta, or slight call it delta T, dt1, and then it goes to T1 plus twice dt1 plus and so on. So temperature changes take place very, very minutely. And after each temperature change, system comes into equilibrium by itself. And this therefore is a very, very slow process, not a rapidly changing process. We turn this into this. Heat exchange is small and so on. Now for that particular process, if we were to take this delta S of system 1, part 1, this one, that will be equal to okay, heat change in each case will be all right, this will be equal to integral from initial to final state of dq by t by definition, and dq we write as m times c times dt. And therefore this will be m times c times log of Tf over Ti, or T. In fact, I now know what initial and final temperatures are going to be. So let me write those values over here. It will go from T1 to Te, and therefore this will be Te over T1. All right. And delta S2 is going to be again dq over T, this time from T2 to Te. Okay? And this will be again, the second block also has mass m and heat capacity C. So this will be mc times T2 to Te dt over T, and that will be equal to again mc times log of Te over T2. Notice that T1, because T1 was less than T2, so Te is somewhere between T1 and T2. So T1 is less than Te and T2 is greater than Te. Alright? Because T1 is less than Te, therefore this quantity is greater than 1. Therefore log of this quantity is positive. Therefore delta S1 is positive. In this case, Te is less than T2, so this is less than 1, and therefore log of less than 1 is negative, and therefore delta S2 is negative. But what about total entropy change? What about it? Total entropy change is of course going to be entropy change in system 1 plus entropy change in system 2 And this is going to be mc times log of Te over T1 plus log of Te over T2. No surprises here. And I can write this because sums of two logs is the log of the product, so I can write this delta S being equal to m times C times log of Te squared over T1 times T2. Okay? Total entropy change is equal to this. And I can actually then try, we should try and calculate Te in terms of T1 and T2. Unless we do this, we will not be able to go any further. What is Te? Te would be determined by saying anything obscure over here? No. It's all very clear, right? Okay? Okay. Q1 should be equal to Q2. The heat that, Q1 plus Q2 should be equal to 0. Heat going in from this situation into this situation should be the same as heat going in from this situation into this situation. All right? So Q1 plus Q2 should be equal to 0, and Q1 is mass times C times Te minus T1, and this plus mc times Te minus T2 is equal to 0. And this tells you that Te actually is equal to, no surprises here, T1 plus T2 over 2, an average of the two. No surprises. If you mix them up, temperatures are, average temperature is going to be T1 plus T2 over this. Now, I will use that in this expression, in the expression over here. So, I have therefore delta S, total S, change in total entropy of the system is m times C times log of Te squared is T1 plus T2 whole squared divided by 4 T1 T2. Okay? And I can write this as mc times log of I can write this inside as 1 plus okay 1 plus T1 minus T2 whole squared divided by 4 times T1 T2. Okay, what I've done is that I've taken T1 plus T2 whole squared over T1 4 times T1 T2 is equal to 4 times T1 T2 minus or plus T1 minus T2 whole squared. And you can convince yourself that this is what it is. Okay? Those of you who have wondered over what I wrote over here, this is what I did. I converted a plus b whole square is equal to twice ab minus a minus plus a minus b whole square. So this is what I did over here. Okay? And when I expand this, there will be minus 2 t1 t2, which will make it plus 2 1 t2, which will give you this. So in this expression, this I can write this down as 1 minus t1 minus t2 whole squared over 4 t1 t2, and 1 plus. I can write this as this, and this is what I did. All right? This is what I did over here. So this quantity is equal to this quantity in the bracket over here by this particular process. I'm erasing it now. क्या हो गया? हैं? All right. So now this quantity, everything is positive on this side in this quotient. So the thing in the bracket over here is greater than 0, greater than 1, and therefore log of this quantity is greater than 1, and therefore this is greater than 0. Log is a positive quantity. Log of something greater than 1 is a positive quantity, therefore everything is a positive quantity. Interesting thing is that delta S1 was positive, delta S2 was negative, but the total change in entropy is a positive quantity. Entropy of the total system increases. Go back to this expression over here. Go back to this situation. You had two blocks at different temperatures, and you brought them into contact with each other. The process of heat flowing from one block to the other is a process which increases entropy of the total system. Nothing else. There's complete isolation over here, complete insulation, and therefore there is no other thing changing. What is changing is the temperature of these two blocks, and this process of exchange of heat, a rise and drop in temperature causes the total entropy of the system to increase. Now, we said that this was an irreversible process. Okay? And we just saw that total entropy increases. So I'm going to therefore put over here that entropy increases in irreversible processes. And I will put over here before this entropy, total entropy increases in irreversible processes. And I will turn this into a law by specifically saying that delta S is greater than or equal to 0. I'm just trying to turn this into a law of nature by saying delta S is greater than 0 for irreversible processes and equal to 0 in reversible processes, and delta S cannot be never in isolated systems. Delta S can never change negatively in isolated systems. So I'm therefore enunciating a law of nature before. Yes?
What I want to ask is that after performing that quasi-static process, we have converted the irreversible process to a reversible process. That's what you said. So how does this law then hold for an irreversible process? It should now be a reversible process.
No. This was, okay, the point that he's making is that when you obtain this result, you actually solved it by turning this into a reversible process. And even for a reversible process, if it was a reversible process, you would get a delta S going to positive. This is the point of confusion, right? Okay. It should be seen in the following way. The process was turned into a reversible process. Where is it? Where is that board? Over here, right? Okay. It was turned into a quasi-static process. Quasi-static process allows, in a process very slowly moving, allows you to treat it as a reversible process. But the total process which took place, quasi-static process sort of is one process divided into 1,000 processes in sequence. Okay? Each one of them going in a not in a non-equilibrium way, in an equilibrium way. But when you take the totality of them, okay, that was the way of treating it. But when you take the totality of them, you have actually an irreversible process. So in each of these small sections, processes, there was perhaps, a very minute or perhaps insignificant change in entropy. But when you take them overall, there is this significant change in entropy or increase in entropy. Have I answered your question? Okay. I think time to stop, time to sort of get into discussions now. I may have been obscure at various points, so questions? Yeah. Yeah. Red lines.
When you are talking about the closed path, whether it's for the heap or for on which curve or on which path we are talking about, we come back to the initial point.
You will need to say that again. I didn't quite understand.
Get it about which path we are talking about. Right? Because when you are getting closed in the closed path of the we are talking about which path.
All right. In the first case, the top lines written in purple, you're talking about those lines, right? And your question is, when I say that it goes in a closed path, what kind of path am I talking about? Is it a specified constant V, constant P, or whatever? Okay, and I think the point I tried to make over there is precisely what you're saying, that the first thing will certainly depend upon the path, the first line. The second line I showed wouldn't depend upon the path. So what I tried to do by this over there is, and therefore I said in the first line, is indeterminate until the path is specified. So I said, in general, you will not be able to determine it unless you know what path you have taken. Okay? Q is a quantity, Q and W, actually both of them, are quantities which are areas under the curve. So if I were to draw a diagram, PV phase diagram, I could draw some other phase diagram. In this picture, if you go from point this to point this, then, and if you go this way, then it is this which is the value of Q, if you want to calculating the value of Q. And if our work, total work, is given by this. if you were to go not this way, but some other way, this way, then this will be the total amount of work that is done. And therefore, if you go this way and come back this way, you actually are doing this much amount of work. So it is the area enclosed by the curve, by the closed path, which will give you the value of Q as well as W. All right. And in the second case, I showed that you don't need to specify a path. You can do without it. So I don't know if I have understood your question correctly and answered it properly or not. It's okay? Your full point of view. Yeah.
So in the second step or third step, we are taking the value of internal energy to be CV dt.
Yeah.
So it means that it is at constant volume.
Right.
Then dW, shouldn't dW be 0? Because at constant volume.
Okay. The question that she is asking is that in this expression over here, I wrote du equal to this, which is for constant volume, and shouldn't that mean that I should take this equal to 0? All right? This is the question. And I think this is precisely the reason for writing down this expression and repeating this point was because I said that u is a state function. And for a state function, you will have values specified at points. There's u1 here and u2 here. And du is a difference between these 2 points. Doesn't depend on how you go from one to the other. Okay? So this is therefore true for not just for constant volume, but for any process. All right? You will take that to be the case. I think this is what we used in the case of calculation of entropy also.
So is every quasi-static process reversible?
Is every quasi-static process? Yes. By definition, quasi-static processes would be reversible.
I couldn't get why would this not be reversible then? Because you defined it as a quasi-static process.
Yes.
And then you found that the entropy came out to be positive. I couldn't understand you answer.
Right. So the point was that in this particular case, the quasi-static process in each of these units, the situation is different, and overall it is different. Overall, you have gone from this situation to this situation, and going from this situation to this situation is irreversible. You mimicked that by taking a quasi-static process and obtained the result which would be valid for this situation. Okay? So the lesson that we learned from this and from the example that I did in the last lecture is that for state functions, if you can't solve the problem in one way, you can always go and solve it in another way, because they do not depend upon paths. Okay? That is the lesson that we learned from these 2 exercises. All right? Questions? Sorry?
If del H is less than 0, that is a kind of empirical statement because you didn't prove it.
I didn't prove it, no. No, I didn't prove it. And if I say that delta S is always greater than or equal to 0, it stands proved that this is negative. That this is 0. True, right? No?
No, you didn't say that as well.
Oh, I didn't. I see. The processes can be reversible or irreversible. Either reversible or irreversible. And since I have taken this statement for both reversible and irreversible, there is nothing left. So this is not possible. So you're not happy with that answer?
You didn't prove that for all irreversible processes it is 0.
Oh, I didn't prove it for all irreversible processes. Okay. Now the point is that no, you only take 1 or 2 irreversible processes and prove in very general sense, and then draw some conclusions. Okay. the irreversible process that we took is a very typical irreversible process. And one can take a few more irreversible processes and show this thing. We took actually two irreversible processes and showed this. Okay? Two quite distinct, quite different. One simple expansion, the other one heat flow. And we showed this, and this is what we made the statement. Okay? The other part sort of stands stated just because that part is true. But I don't know. Let me think about it. Let me see if there can be a logical proof of saying that delta S can never be negative. Okay? There was a question from that side somewhere? No? No? Okay. All right. Let us move on. I will now go to do an exercise which should be instructive in telling us how we can do some calculation in calculating, do some calculations of change in entropy. In a situation which will be interesting. All right. Take this good example. I think this is a very instructive example of change in entropy in an irreversible situation, and actually dealing with numbers, trying to calculate things. So you take an ice cube and drop that ice cube in a bowl of hot water. Certainly many things will happen. There will be heat flow. The hot water will provide heat for the ice cube. The ice cube will melt, and the water of the ice cube will attain certain temperature, and the hot water will also attain certain temperature. There would be kind of an equilibrium temperature between them, and we need to. From that example, we will try to calculate rise in entropy or the total change in entropy. So, ice cube, let's take mass equal to what? Usually about 10 grams for an ice cube. Okay, about 10 grams. Say initially at temperature equal to minus 15 degrees centigrade. And we drop it into a warm water. The mass of water is, I have taken 100 grams. And I have taken initial temperature of this water to be 15 degrees centigrade plus 15 degrees centigrade. Okay? And put them in a proper enclosure. There is no other environmental contribution to this particular process, only heat exchange. And we need to know the heat capacity of ice that is given to us. It is 2220 joule per kg per degree Kelvin. This is nearly correct, nearly the right number. And heat capacity of water is 4190 joule per kg degree Kelvin. But then ice will melt also, and therefore there has to be we need to know the latent heat also. And the latent heat of either fusion or solidification is given as 333 kilojoule per kilogram. It's very interesting, you know. Latent heat is pretty large, and in quantity. This is only 2,000, this is only 4,000, and this is 330,000 joule. So it is about 100 times larger than the heat capacity. So the amount of heat that you need to raise the temperature of water, this is about water only. Water over a certain range of temperature would be given in terms of the heat capacity. But when you, melt an ice or a block of ice or freeze water, then the amount of heat you need to extract or to give is nearly 100 times larger. And this is what we commonly use in our daily life everywhere. We make use of this fact that there is that heat content in substances somewhere that we can make use of. So we sprinkle water during summer days so that there is water evaporates, and as it evaporates it takes out a lot of heat from there. Or we use these desert coolers. Desert coolers work on the same fashion, that the water evaporates, and as it evaporates, so much of the air coming in, the water evaporates, and so much of heat is taken away. Things cool down, and you enjoy that. Similarly, in other situations where you use this, our perspiration process is the evaporation process. So evaporation, condensation are all those processes which happen all the time around us, and we all know. But that is because of latent heat being such a big, what do you call, bank account, large bank account, where you have a large amount of heat stored. All right, here we are. We have therefore, how many processes do we have? In the last 10 minutes, I think I'll be able to finish this. We need to find the final temperature. But we assume that final temperature is greater than 0 degrees centigrade. We will find out. So, total heat.
लेटेंट हीट ऑफ फ्यूजन सर हम इसलिए ले रहे हैं क्योंकि हमें पता है 0 डिग्री से ऊपर चला जाएगा, मेल्टिंग होगी. हम अगर हमें इस वक्त अगर ना दिए होते टेम्परेचर, हम कहते हैं कि एक वाटर बाथ में डाल दिए, तो कैसे कंसिडर करते कि वो मेल्टिंग होगी?
ओके, वी डोंट नो. हो सकता है कि this thing may come out to be minus 3 degrees centigrade. In that case, we will certainly not need it. But we will need it, because the rest of the water, this water, will turn into ice. We will still need it. Okay? And it will be needed. All right. So we have to take care of the following things. Number one, ice going from minus 15 degrees C to 0 degrees C. All right? Ice temperature has to go up from minus 15 degrees centigrade to 0 degrees centigrade. Then second, ice melting to water at 0 degree centigrade, going into water. And the third process is assuming that TE is larger than 0 degrees centigrade. Assuming that this is the case, then this is the situation in which the melted ice, which is water, goes from 0 degrees centigrade to the equilibrium temperature TE, and water, warm water, comes down from 15 degrees C to the equilibrium temperature TE. Alright? All these things will take place one after the other. And we need to calculate these things. In the first case, the contribution is, the mass is equal to 10 grams. 10 grams is 10 to the power minus 2 kilograms. Alright? Ice, in this case, is 10 grams, which is 10 to the power minus 2 kilograms, multiplied by heat capacity, which is given in terms of per kilogram. So it is multiplied by 2220 joules per kilogram. So kilogram cancel out. It is now joules per degree Kelvin. And then multiplied by the temperature difference from this to this. And what should I write over here? Not converting into Kelvin? Which is the same. Okay? So 15 Kelvin. So this Kelvin also gets cancelled, and therefore you have only joule over here. Next, mass times latent heat gives you the amount of heat that goes into melting ice, and divided by mass times that will give you this, which is 10 to the power minus 2 times 333 times 10 to the power 3 joules per kilogram, and per kilogram cancel out, so this is again joule. The third part is when you have water, the mass of this water is the same as the mass of the ice cube, which is 10 to the power minus 2 kilogram. Oh, acha, okay. 10 to the power 2 kilogram. I will try and make it bigger in the next. All right. Not much time to go, so I can perhaps spoil one board. 10 to the power minus 2 times 2220 times 15 plus 10 to the power minus 2 times 333 times 10 to the power 3 plus 10 to the power 2. Now we are talking of the process where this melted ice with mass 10 to the power 2, 10 to the power minus 2, 10 to the power minus 2, it rises up in heat, gets heat to get to temperature TE, and therefore heat capacity, which is the same as the heat capacity I wrote earlier, which is of water. Heat capacity of water was, it is 4190 times 4190 times, now the temperature is difference is again TE minus 273. Okay, it goes from 273, which is 0 degrees, to 15 degrees centigrade, to the equilibrium temperature, not to 15 degrees. And then lastly, I will have this total mass, which is 100 grams, right? 100 grams is 10 to the power minus 1 kilogram. Why did I write this? Okay. All right. 10 to the power minus 1 kilogram multiplied by water's ice, this is 4190, and then multiplied by TE minus 15 degrees Kelvin is 288, and all of that should be equal to 0. You solve this and you will end up by saying that TE is equal to 278.7 Kelvin, which is 5.7 centigrade. All right? The last bit is when you try to calculate delta S. Again, in delta S, you will calculate in the first process ice going from minus 15 to 0 degrees centigrade. This is a process in which this heating takes place in an irreversible manner. We will have to change it to reversible the way we did earlier. Is that okay, or am I? Yeah.
That would be 288 minus T.
The sign will take care of itself. Whether the heat goes out of the system or into the system, that sign will take care of itself.
Since the equilibrium temperature would be lower than that.
Yes, and therefore the sign of heat will be different. So heat going into the system is plus, coming out of the system is minus, and that will be taken care of. So what is this excitement? Everybody is talking something. All right? Either I just give it to you as an exercise. Go ahead and do this exercise. And then I will go and sleep. Okay? Delta S will have to be, in the first case, it will be Mi ice C ice log of Tf over Ti. In the second case, when you had the heat of fusion, when there was a fusion of ice would amount to saying that latent heat Mi times L divided by T. T is 0 degrees centigrade, which is 273 Kelvin. In the third case, you will have again the same ice, but this time the heat capacity of water I'm quite amazed. For some reason you find this very not very serious. Why? This is either it is very trivial and I just leave it here and let you grapple with this, or let me just finish this calculation and try and see what comes out of it. I am taking you through some calculations that you will eventually go through in your recitations and in your exercises, in your assignments. And I am trying to make sure that when you do that, those things, you are reminded of how this is done. And this is why I am going through this specific exercise in this detail. So I hope you will bear with me in the last 2 minutes or so. This times log of these two temperatures, which will be TE and T ice, which will be 0 degree Kelvin, 0 degrees centigrade. And in the fourth case, you will have mass of water, heat capacity of water, and log of TE divided by the initial temperature of water, which was some initial temperature Ti. I have this over here. I'm just writing this as log of 273 divided by 258, just to avoid any confusion. Here this will be 273, and here this will be TE divided by 273, and here this will be TE divided by 288, and TE we have already evaluated. All right, so you can substitute this or all this in, and you will get change in entropy is equal to 0.568. All right, so the point that comes out is that in this particular process also the total heat capacity is positive. This is an irreversible process, and it's a positive quantity. It is not zero. It is not a reversible process. I will stop over here. And question?
Yes. Sir, it is related to the previous concept of delta S being positive always.
Related to?
The previous concept of delta S being positive always. If we have a small object of particular material, and then we move it into a heat bath, and then it will acquire the temperature of the heat bath, and its own temperature would then go to. If we assume that the initial temperature was greater than that of the heat bath, that would essentially mean that delta S is negative.
In that case, yes. Locally, as I said in the other example that I calculated somewhere, I don't have it in front of me. Yeah, here. For example, in this case, the entropy of one system is positive, the other one system is negative, but the total entropy is completely positive. So it is possible that because of heat flow, the system gaining heat will have a rise in entropy, system losing heat will have a lowering of entropy, but overall there will be a positive increase in entropy. All right? We can discuss it separately later on.